Alright, so guys, what's the general rule for solubility? How do we know if something dissolves in each other?
Like dissolves in light.
Right, like dissolves like. So dumb that down for me. What does that mean?
Like polar dissolves polar, non-polar dissolves non-polar.
Right, so we like to say like dissolves like, but then sometimes you just need to elaborate a little bit. And that's the polar dissolves polar things, non-polar dissolves non-polar things. What things don't dissolve each other?
Polar and non-polar.
Polar and non-polar, right? They just don't interact very well. They can interact really weakly, like you guys saw in the intermolecular force exercise yesterday. They can interact a little tiny bit with London dispersion, but it's just not very strong, and so they don't really interact well. So we know this, okay? Water is what? Is it polar or non-polar? Polar. That we've seen that maybe 3 or 4 times, so that's one that I'm guessing you're accidentally memorizing. And then what types of things would dissolve in oil? Non-polar substances. So with water, what is its structural shape? What does it look like geometry-wise? It is bent, so draw that for me, and we're going to draw water boiling. So that means we're starting with what phase of matter? Liquid, and we're going to what phase of matter? Gas. Gas. Okay, so we know water has what atoms in it? How many H's? 2 of them, H2, right? So H2O. Remember, you always start off with looking at your valence electrons. There are 8 there because there's 2 from water, or 2 from H's, and 6 from oxygen gives us a total of 8. So I'm going to draw it like it looks versus drawing it linearly, because I can draw it looking like a dinosaur, but if that's not the molecular geometry, we can't call it out as that. So this is water, and it's going to boil, right? So what do I need to indicate is happening as I'm going from liquid to gas? What's happening? Is it a chemical change or a physical change? It's physical change. So can the structural format of water change? Why? Because it's a physical change. You just got back to where you were, right? So why can the structure of water not change in a physical change? Anybody? You're not changing any of the chemical structure. You're not changing it chemically, like you're not changing its chemical bonds, for example. So what I can do is I can show water interacting with water. Okay, so there's 2 water molecules. How do they interact? Okay, so we have 3 intermolecular forces, right? So with those 3 intermolecular forces, we identify that this is a what kind of molecule first off? Polar or non-polar? It is polar, and then polar molecules that can interact via what or what? Dipole or hydrogen bonding. Those are our 2 choices, and then I narrow it down from there. Once I know it's polar, I narrow it down to dipole and hydrogen bonding. How do I know that this is going to interact via hydrogen bonding? There's an H bonded to a O in the structure, right? H bond or fine, right? H bonded to F, O, or N. So where is the hydrogen bond occurring between Wesley's table? What part of water molecule number 1 and number 2? This is a partial, because hydrogen's totally not electronegative, right? This oxygen's partially negative, okay? So that's kind of the opposite subtracting, and then we can show that with a, how do I show the hydrogen bond? Little dash line, right? So just, there we go. So I can multiply this by 1,000,000, right? But right now I'm showing this liquid because I'm showing them kind of close together, and I could show this interacting with another water molecule and this interacting with another water molecule, and I can do this over and over and over again. And so that's going to create a big liquid pool, and then as I allow it to heat up, what point does it get to boil, temperature-wise? 100 degrees Celsius. So what's going to happen to this water molecule as it boils? They what? They just get farther apart. So does the structure change? No, it just gets farther apart. So I can draw 1 here. Here's water molecule number 1, and I can draw 1 down here. Okay, so what have I done with the intermolecular forces? They were close together, and they had some hydrogen bonding action going on. So now what's happening with them? Do they even know the other one exists? They're so far apart. Are there any intermolecular forces occurring between these 2? Not at all. So what we've done with this temperature change is we've overcome the attraction they have for each other. We've sped them up so much they started to spread out. So that's what we're talking about when we talk about the boiling point, right? How strong are the attractions? If there are super strong attractions, what happens to boiling point? It increases, right? It's got a high boiling point. And what happens if you have really weak attractions? You look at it with an angry face and it's going to start to boil just because it's not going to require much energy to pull them apart. So just remember the structural change, or the structure does not change. All right, review metallic real fast. You guys in your tables come up with at least 3 properties. You might have your table with you. You can use that. All right, come back to me. 3, 2, 1. Ariel's table. Shout out 1. Okay, so malleable and ductile. Malleable and ductile is very different than what we do with ionic bonds. Maverick, screw, tell me another. So inside of the metallic bonding area, there are some positive charges. Okay, I'm going to elaborate with that with maybe another group. Give me a group. Okay, they're conducted to what? Electricity? And heat, right? So thermally conductive and electrically conductive. Admir's table? No, sorry, I already got you guys. Riley's table. Solid room temperature. And same people. Elizabeth's table. High melting point. CJ's table. Don't dissolve in water. And final table. Say again? They're shiny. Okay, perfect. All right, so we'll talk about the electrons because it doesn't sound like anybody mentioned the electron mobility. That's a piece that we're going to add to this. So, I'm going to come back to this. We'll play Kahoot in about 10 minutes, okay? So, this is a lot of information about metallic. Read first, write down the key things, and then I'll discuss, okay? Because we haven't seen metallic in like a week. Just going to try to get to review metallic. You can add this to your warm-up notes. You can add this to your notes. All right, so on this on these 4 bullet points here, there are some key words. Notice that I'm calling it a metallic bonding theory because it's like the theory on how metals interact with other metal atoms, but it's not really a bond. Like an ionic bond is a positive and negative ion attraction, where a covalent bond is a sharing of electrons in the middle of the 2 nuclei. It's more of just an attraction. So it makes it very fluid. It makes it have a lot of unique properties because of its interparticle attraction. So that interparticle attraction is kind of one of those key words. So what we can do is we can have metals on metals on metals interacting, but they all don't have to be the same metal. So we have examples where we have metals interacting with different metals, or metals interacting with non-metal, I won't say non-metals, things like carbon, but we create an alloy. So see if we can come up with a couple examples of alloys. What's your tables? Maybe one or two. It's metallic-like, but it's not truly a metal in your table. Corbin, you got one?
Bronze.
Bronze, another one. Bronze, say again. Steel. Brass. Copper itself is in metal. It is a metal. That's a good list. That's plenty. So what you'll notice is that these are not on the periodic table. These are blends of metals from the periodic table that are not on the periodic table. Okay, so how does a metallic bond work? We have electrons floating around very freely, but those electrons are still attracted to their metal ion atoms. So the valence electrons from all these metal atoms kind of are put in a pool, and they can float around very freely. We call that delocalization. So if I am localized, what does that mean? You are localized in Nazi, you are in one place. So if you're delocalized, what are you?
Not in one place.
Not in one place. That means that you are not, I'm basic, right? Not in a single location. That means that they can freely float around. Now, because they're still floating around, you're like, oh, they could just go anywhere. No, they still have their attraction to their metal core, which is a cation. So there's still an attraction aspect to it. So we call that a sea of delocalized electrons. Can I move on? Almost? Okay. So a sea of delocalized electrons. Like I said, please write down keywords. If you want to print these off beforehand, you can. All right, so what do we see in this image? Who's the cation? Who's Ag? Silver. Silver is Ag, and you can see all these electrons floating around it. And then over here, you just see a cation, and you see all the electrons are moving around it. So what do you think these electrons can do? What can they do? Float. They can move this way, they can move this way, they can float around, and that gives them all kinds of characteristics that are very, very unique to metallic bonding versus like ionic bonding where they're static and they can't move. So because those electrons can move, that gives them these properties. Conductive, we talked about the thermal and the electrical conductivity. If electrons are mobile, they can move. It allows for current or energy to flow. That's all conductivity is. If electrons are able to move, you can pass a current, like electrical charge or heat energy, through them, and they carry it on to the next one, to the next one, to the next one, to the next one. That's why maybe after 5 minutes of cast iron skillet being on the stove, you do not want to touch that thing, because that has already allowed all the energy to transfer through it. Now, malleable means you can do what? Say again? So, not into a wire.
Sheet.
Flat sheet, right? So you can hammer it into a flat sheet. And so, if you can hammer it into a sheet, this has to be related to the mobility of the electrons as well. So let's say you've got like a little just bundle of positive, 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 negative, 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 right? Now, are those negatives, do they need to stay in one place for this metallic bond system here? Yes or no? No, they are able to flow, and they can be attracted to this one, and then to this one, and then to this one. They can kind of flow freely. So if I'm hammering it, this is a hammer. Yeah, it's a hammer. You hammer it into one sheet. What's happening is as you flatten it out, the cations kind of line up, and then the electrons just surround them, And so they just mush themselves into a flattened sheet. That's it. So they're mobile and can move. There's not really any other way to explain that. They can move, they can flatten themselves out. And it's still very stable. Why is it still really stable, just like this is really stable? Why is this just as stable? What's happening with those targets?
They're still adjusting.
They're still attractive, which means they're still stable. Draw out the ductility. Okay, how are you guys drawing the ductility? What is it forming? A wire. So this is kind of working the same way. As you pull it into a wire, left and right, the electrons line up with the cations and it creates a very stable system. And so they kind of fill in the gaps. If you start to stretch it too far, you know, you can like think of like Play-Doh. If you stretch it too far, it breaks in the middle. Instead of breaking in the middle, the electrons or the cations will move to create like a solid structure. There's not going to be any gaps where it would break. Eventually, yes, it would, but that's not what's going to happen too immediately. So this is a little different. Oh, when are metals conductive? In what states of matter? Solid and liquid, and if they could be gas, if they were volatile enough, they'd probably conductive in their gaseous form as well. But they're basically always conductive, right? When are ionics conductive? Molten, which means liquid, and dissolved, what's the word for dissolved in water? Aqueous, right? So in contrast to ionic, which is only conductive in molten and aqueous, which means dissolved, these are only going to be conductive in these forms because the electrons are free to move in those forms. And otherwise, in solid ionics, are the electrons free to move? Yes or no? I got two people participating. Let's work together here. No, so they can't move. That means they're static. Static means they can't move, which is why it's non-conductive in a solid state. That's ionic for you. Okay? Give me a thumbs up when I can move from here. So this is a quick review of metallic, but I feel like you guys already knew the characteristics, which is explaining why the structure plays well into those characteristics, so why the structure relates. So some of those alloys you guys just named off were valid. Here's a couple more. Remember, alloys are just a blend of two or more metals, maybe one of which, or sorry, at least for one is a metal. You can have some where you have some non-metals blended. It's not bonded, it's a blend. So who has this cast iron skillet at home? Or you've seen one. Okay, you've seen one someplace. It's a blend between, so it's trying to say cast iron, so it's saying it's iron, but it's blended with something else. Carbon is embedded there, okay? And in bronze, like the Statue of Liberty or the bronze statue of Dale Earnhardt in Kannapolis, who's ever seen that? Okay, if you've been through K-Town, you've seen it, okay? Then it's copper and tin blended together. Why are we blending metals? And why are we blending these things? Just because we got free time? Why do you think? Corbin?
To make a stronger metal.
Okay. So we want to maybe increase the strength. What's another reason we might want to do that? What about that? Why would that be beneficial to us? So you want to enhance one property, whatever that property is. Let's think about some of those properties. We've all, like, the Olympics are just on TV, okay? I know it was like 2 a.m., but maybe we've seen some of the Olympics. What do they do with the gold medals when they get them? They bite them. What do they show about gold when they bite them? When they bite them, you see like teeth marks in it, right? But they can bend it. You've even seen maybe somebody bend it. What does that show about gold? It's very soft. Who wants like some gold jewelry or a gold ring or I don't know, some gold rims if it's going to be soft, right? That wouldn't be very durable, would it? So that's what we're talking about. We're trying to change the properties so that they're more durable. So the property that we want from gold is, oh, it's pretty, it's gold. But when we blend gold with something else, we're making it more durable. So we might strengthen it by decreasing the softness. Or we might increase the shininess. or we might decrease the reactivity. There's a lot of things we want to do with metals to either make them more durable, make them last longer, and that's what we're going to do that by, is by alloying or making an alloy. So we've all seen copper. Copper within the Statue of Liberty. Okay, that does not look like copper. Why is she green? It's oxidized, but what's the name of the green stuff, that flaky green stuff on the outside of the Statue of Liberty? It's not rust. Rust would be like an orange-brown color, which is from iron rusting. Copper rusting forms something else. It starts with P. Doesn't you know it? Just saying your fun fact. Trivia knowledge. I would not want you on my team for trivia. Okay, patina. It's called patina. She has all kinds of patina on her, which is oxidized copper. Oxidized copper. Okay? So, in this case, copper, what color is copper normally? It's copper colored, right? So it's browny, kind of shiny orange. Red is beautiful. That is not really what we're looking for when we say copper. So what they were hoping to do when they made this alloy, they blend it with tin. Tin also has like kind of a shiny, orangish, tannish color to it. They were hoping when they blended these, they would decrease the reactivity. Well, you can see it worked for a while. Like a long time ago, she was not this color. But copper is super reactive with air and water, and so it forms this green patina. Tin is not as reactive, so they hoped when they blended it, she would last forever. Well, she's still lasting, she just changed color. So they were hoping that they could create a system where it would not erode so quickly. And then cast iron. Iron, we know itself, like what did you guys just say forms on iron? Rust, right? Iron is pretty reactive too, and it forms rust. Who wants to eat rust in their cast iron skillet? Nobody, right? So they blend it with carbon, 1, to decrease the reactivity, and 2, to help it hold heat better. Carbon holds heat better than iron does. Iron lets heat flow right in and right out. It goes away. So you can touch like a cookie sheet within minutes of it coming out of the oven, right? Not immediately because it'll burn you, but you can touch it within probably 2 or 3 minutes. But cast iron, you can't touch for an hour because that thing is holding on to heat really well, which is beneficial for what century would want something to hold on to heat really well? Now or 1700s? Because they didn't have what?
Fire.
They didn't have what? They did have fire. They had wood stoves, and they wanted to keep their food hot all day. They did not have electricity. Okay, so in terms of carat weights, okay, so we've all heard 24 karat. 24 karat. I'm not going to sing it, but what does that really mean? 24 karat what? Magic. Gold, right? Yeah. So we've heard 24 karat, 18 karat, 14 karat. Which is the best? 24. Why? Okay, so it's the best because it's the most expensive, or it's the most expensive because it's the best. You know, who came first? Yeah, chicken or the egg here. What makes it the best? What makes it the best, guys? It contains more gold, a higher percentage of gold. Okay, so higher percentage of gold. All right, so basically we're not saying it, but we're thinking it. If it's a higher percentage of gold, that means that there's something else in it, right? So this one has a mediocre percentage of gold, smaller and smaller. What else is blended in? Gold. Here it is. You've got gold, or to make like something called white gold. We've all seen white gold and yellow gold and rose gold, and yep, that's about it, okay? You got silver, copper, and gold blended in them, okay? So in terms of an alloy, we've made an alloy, and now we're claiming their, higher percentage of gold, mediocre, and then smaller percentage of gold. But this is what the blend is in the alloy. Now, if it were me, I would not want a 24 karat gold piece of jewelry. Why? I don't care if it's expensive.
Heavy.
No, so it's not dealing with its heaviness. We totally just talked about gold. It's soft. Okay, so I played the baritone in 8th grade. I'm not proud of it because I was no good. And I carried this baritone. I had this ring from my grandpa. And I'm in middle school to high school, my mom taught. And my ring became black. What do you think my ring was made of? Gold. Like pretty much pure gold. First of all, pure gold reacts with skin. It creates like a greenish tone to it. Like nickel, who's ever seen like nickel-free earrings, things like that, because it turns your ears green because it's basically oxidizing your ears, or the metals depositing in your ears. So you really don't want this because it's going to be super, super soft, okay? You'd rather have things that are like 14 and 10% gold because, I don't know where my little doodad is here, but these are going to be decreased percentage of gold, increased percentage of like silver or copper. These are less soft, so these are more durable. So what pieces of jewelry would be okay for us to have 24 karat gold with? What pieces of jewelry would be okay to have 24 karat gold? Earrings, because you're not like bearing down on your ear and bending your earrings all the way, right? But if you have like a necklace or rings or other things that you would use in a daily life, you want more durable pieces of metal, and that would be better to have 10 or 14 karat because they're stronger. Okay, so guys, girls, start buying jewelry for other people. Tell them why you got the cheap 10 karat gold. Okay, tell them. Say this will last longer, honey. Don't worry about it. They don't care. They want it to last. Okay. All right. So what we were intending to do today was our brass penny lab, where we're going to blend alloy some metal to make gold, which is brass. It's not really gold, guys. It looks like it. But here's the deal. When I'm out, I expect you to be more perfect and pristine with the subs than when you are here with me. So after I talked to the subs some more, I had many concerns. One, cell phones are out. One, no cell phones are out. You can see right here it says BOIOT stoplight on silent or vibrate. You didn't use your cell phones whatsoever yesterday. Why? Because you had your laptops, right? I'm not yelling at the whole class. I'm just talking out loud about expectations. So two, you were supposed to work with a partner, and he told me that there were some groups that were getting kind of chatty, talking across tables, and not on task the whole time. I think I know who that was. But and three, when I came in intervention, many of you guys were very much on task working on your Unit 2 corrections, and then you sat there afterwards and did nothing. Okay, I am graciously saying the quizzes on Thursday. We're basically done learning content. And metallic bonding is the only thing we need to really review about why the bond properties existed. I could have done nothing today, but I want to give you guys some time to practice from the tutoring, whatever that may be. So, we're going to do our lab whenever we have time. My 4th period is in the lab because they were on task. Now, they were with me. But we had the very first day of school, my little expectation sheet. Remember that? I wasn't here either, but you guys did a good job with that. I'm expecting that you are pristine, you are perfect in all ways on days I'm not here. This class should be able to be productive and run on its own with no sub. So I'm expecting that, one, you don't lack of sub and say, I'm using my phone as a calculator. What was your calculator yesterday? Counting chance electrons? You got 10 fingers and 10 toes, you can do that with. Okay? So I'm expecting that you're better, because if I'm out again, but I have other responsibilities in the county I have to do. I'm a teacher leader in 8 schools right now, so I have to go help other teachers sometimes. So I'm expecting you're good. Got it? Okay, so we're going to do a different activity today to still prepare us for our quest tomorrow. And we will do our brass penny lab. It's just not going to be today. Okay, so hold on to your pennies. Okay? Do me a favor. Grab laptops. This half room, go grab laptops first. We're going to play Kahoot first. So you know who you are. If you have questions about anything I just said, you can come talk to me later. And then second half of the room, if you guys will go grab your laptops, please. That first, that's probably easier right there. So while you're logging on, we're going to kind of pause the video for 2 to review, but then again, I'll just tell you to log on. you have a bunch of papers, you can give me some, I can help. Yeah, I wish you Alright, got 6 of us in here. I got 18 of us. Okay, so listen as we go here. In terms of what to expect for tomorrow, this is a brief explanation, okay? You have, it's like 6 or 8 multiple choice. Sorry, I can picture it, I can't remember it there. So questions like these would be relevant for multiple choice. It's related to properties, related to like electronegativity differences, or what types of atoms are forming in that type of bond, or coming together in that type of bond. I think pretty easy ones, to be honest, but we need to review that piece. And 2, you have your free response section, which is a table, right? Table just like your problem set on 7-8, or like we did it in class on what, Monday, intermolecular forces, that table. So what was the first piece of the table? Draw it. Okay, let's say draw the Lewis dot structure, right? And then we look at the structure and we say what?
Polarity.
Maybe not quite. Let's do shape first, right? So we're looking at geometry, the shape. And then we look at polarity. And now that we're smart and we know all this extra information, from the polarity we look at the IMF. And then from the IMF, boiling point ranking, okay? I'm going to review some of those mistakes on problems at 7-8 after this. Okay, is everybody in? 2 people, 1 person's absent. I'm missing 1 person. Who's not in yet? Okay. 6-1. Just gonna write this up here. 27039. Okay, let's roll. Ionic bonding is. You can't see my scooch. I have a part of the speech, FYI. 30 seconds is too long, really. Okay, most of us did alright. Metals and non-metals from ionic. What would this one be? Covalent. If you can't see, you need a scooch so you can see. A metal metals will donate because most metals have how many valence electrons? 1, 2, or 3, right? So they have less than 4 valence electrons. A non-metal good, opposite, we'll accept. So metals will form, in an ionic bond situation, a metal will form a what charge? Say again? Positive because it lost electrons. A non-metal will gain. I believe in myself that I chose the wrong one. So you just hold on. You just hold on. This is the one I want to do. Yeah, this is way better. Play. I was mistaken on my choice. This is the one I actually, well, this one is the one that will help you tomorrow. You're welcome. I chose the wrong one. I'm fixing myself. Okay. Oh, I have to pick. Good thing I saw that early. Okay. And restart this. Okay, almost done, everybody. And one more lesson. 18, 24, 9, 28. 18, 24, 9, 28. 18, 24, 9, 28. Okay, let's do this again. Which bond happens between an S block metal and a non-metal? Powers to skip you. Should we just pretty fast? Yes, ionic. Metals and non-metals again. First question, ionic. Metals are always try your own so you can assess your own knowledge. This isn't about your neighbors, it's about you. Okay, so I will give credit for shiny metallic bonds form shiny substances. Metals, maybe. But the better answer was that we were talking about ionic bonding, so it's talking about cation formation here. But I will go back and give credit, no worries. Which type of bond shares electrons? And there you go. Okay, there is no such thing as a transition bond, and there is no such thing as a polyatomic ion bond, so good, very little choices there. But sharing is certainly going to be a word we use for covalent, not for ionic. Which type of bond is the strongest, causing the highest of most melting points? Three, two, one, okay. Oh my goodness, no, we went through all this boiling point ranking, and who's always number one? Ionic. And then who was highest of the ionics? Of the ionics, hydrogen bonding is not an ionic. Nope. Who was charged product? Right. When you multiply the charges, whoever has the highest charged product. Which type of bond is between two or more nonmetals? Okay, believe the end. Covalent it is. Covalent is non-metal, non-metal. Why are few elements bond?
I was all of the
Yes, this is correct. Yes, to achieve octet. Yes, because of attractions. Yes, all the above. Best answer, all the above. How can electrons participate in the bonding process between elements? Okay, so again, I think this was just a quick answer, but this one's referring to what kind of bond? Transferring. Here, catch my ion, right? That's going to be ionic. Gaining electrons? Ionic, right? And then sharing. Covalent. What is an ion called that loses an electron? Three, two. Okay, everybody, pretend throw an electron away from you. Throw it away. What are you now? What you are? What charge? Positive. You are cat. Like cats have paws. Positive. I can't really have you memorize that in any other way. No. Shame on you 9 people. Shame. What is the ion called that gains an electron? Catch the electron back and think about what's happening. Do you see this face? This is the side ion, because we just went the opposite one, so you could not have chosen cation again. This was the opposite of what just happened in the first place. So capture the electron back. Capture it. Okay, you got it. You caught it, right? And you are now having an extra negative, and so therefore you are negatively charged, called an anion. Just think how negative that sounds. Anion. All right. Which of these ionic formulas is written correctly with a cation ion first? Use your brain, not your neighbor's brain. Your brain. Three, two, one. Skip. Okay. And, oh, that doesn't matter. Okay, so, first of all, the only thing with anything listed first is this one. All these others are listed collectively together, right? So, process of elimination, red. Two, if it's a cation ion and it's an ionic formula, what has to be in the formula? A metal and a nonmetal. That is a key point. Metal and nonmetal. Nope, that's two nonmetals. That's just a metal. That's just a noble gas. That's the only one with a metal and a nonmetal. So think critically on these, and this is what I would expect you to be aware of for tomorrow. Which of these is a covalent compound? Three, two. Okay, this should be quick thinking. Covalent, you're looking for two what? Two nonmetals. This is iron. We all know that's a metal. This is calcium. We all know that's a. This is potassium. We all know that's a. Obviously, this is the only one left. And sulfur and oxygen are both nonmetals. Moving on. Which type of bond usually results in gases and liquid at room temperature? Three, two, one. Okay, we're gonna go through this. Who puts salt on their French fries? What is salt made of? Sodium chloride, and its part is a rod. You would never have gaseous salt hitting in the face because then you breathe it in, and then yeah, it wouldn't be good for your lungs. So think of it like everyday life items. Definitely ionics are solid. The covalent ones are gaseous or liquid. Which one is is only electrically conductive in molten or aqueous? Three, two, one. You don't get all kinds of time here. All right. We just went over this, right, with metallic. Metallic is, when is it conductive? Always, right? There's no caveats here. Covalent, when is it conductive? When is covalent conductive? Never conductive. Metallic, always conductive. Covalent, never conductive. This is sometimes conductive in these particular states of matter. These are not fun facts. These are like definite facts you should know. Which of these is soluble in water, aqueous solution? Three, two. Okay, so the absolute best answer is ionic, because ionics are going to be interacting with water really well because they have some negatives and some positives and some partial negatives and some partial positives. Polar things dissolve ionic really well. Metals do not dissolve. We drove in the rain yesterday, right? If your car dissolved, we would be walking to school. Like, your car is made of metal. It will not dissolve. So good. And then covalents don't dissolve well. Oil, think of that as covalent. It does not dissolve well. Which has delocalized electrons, creating malleability and ductility. Three, two. All right, so we did okay. That is a metal, but this is a non-metal. Therefore, this is a what bond? Ionic. Right? Sodium is what? Straight up a metal, so therefore it's a metallic bonding situation. That is the one that's delocalized. This is covalent, two nonmetals. Which forms a sea of electrons giving properties of electrical and thermal conductivity. Three, two. Oh, very similar to the last question, right? Who's AG?
Silver.
Silver on silver on silver is going to make metallic bonding happen, which that is the property of a metallic bond. Oh, yay, sorry, on fire. Can we save these? All right, so we are getting ready to have a severe weather drill. Okay, perfect timing, guys, at 9:30.
So whenever we get back, when the thing you do goes off, it's like a weird siren sound. Another class will be filing in here, so they'll kind of be in the front. So if you guys can get your guys under, like, kind of just out of the way. They are going to have the duct cover kind of in the front, on the side, maybe around your desk. We, on the other hand, we know our classroom well. We're going to be filing to the, like, around the lab station, not the input, because that's glass, and not the back area, because that's glass as well. So basically, severe fire drill, or severe, not severe fire drill, severe weather drill, like tornadoes, hurricanes, tsunami, things like that. In Charlotte, yeah. In a tsunami situation, I'm not quite sure. I think we get on top of lab stations. But anyway, for this one, we do have to do the ducking cover. So you have to put your head down and your butt kind of curled down, at least for like a minute, so we can practice that. And the other class will come and do the same. We don't need to talk. You can take a little nap if you need to, but it won't be a very long drill. Okay? I would shut my computer, so just in case anything's in my computer off, I'm not listening to talk. So I'm expecting this to happen in like 30 seconds. So think about bonding. Think about bonding.
And I'm waiting, and if they waste my class time, I'll be mad. Where's my cell phone?
Well, I will do this while we wait. Let me just check that email real fast. Nothing important, okay? So listen up for tonight. And actually, we're going to get this started in class shortly. We're going to do our close reading for this unit, which is related to bonding. So I have 4 articles: sticky glue, sweet candy making, electronegativity, and paintball. Okay, so one of you guys will get one of each of those. So I'm just going to start out per table, giving you guys one of each, and that way tomorrow you can branch off from our tables. Okay. So 1, 2, 3. Let's get one of those per table. Okay. You got it? One of those per table. Do not take more than one per table.
Good morning, Charter family. At this time, we are moving into drill procedures. This is a tornado drill. Teachers and students, please follow the procedure for a severe weather drill, which is the tornado drill. At this time, again, please move into your appropriate location for the severe weather drill. We will inform you when the drill is over. Thank you.
So I would say line up here, kind of around here.
Are we allowed behind there?
I'm not getting in that position.
Knees are on the floor. Your head is down, and you are crouching forward like this. Your back is up. Let's go. We need to practice You don't want to look at your successfully strike out. Sit down on your butt and be quiet.
Because I don't touch people.
You
gotta be quiet. We're just waiting up because
You need to be talking in the box. Where are you? I don't see you. Be quiet. Make notes yourself.
You got Yoda.
It's great. About to get attention. Come on, work with me. It's just
because trees were trying
Should we go to Mall Creek?
Good morning, Chargers. Thank you very much for your cooperation and participation in today's severe weather drill. At this time, we return to class. And thank you for your participation in today's severe weather drill. We may now return to class.
All right, guys, let me finish passing these out first, okay? So keep passing those around so that, where do they stop?
Over there.
Maverick, pass those out, guys. Okay, so there's one, there's one, what was that one? Glue. And then there's going to be one, this time around here needs a hut. Thank you. Alright, so there's going to be one candy making per table. That's coming around now. There's going to be one electronegativity sheet per table. That's coming around now. And then there needs to be one paintball per table. Now, I know that there's more than 4 of you. And less than 4 of you. No, actually. Yeah, we're good. So at this point, everybody should have one, and you'll have some extra floating around, okay? Where are my big stacks? Okay. Any extras? Guys, listen, this is a pretty simple process. At each of the tables of 4, okay, raise, you can do that now. Raise your hand if you have paintball. Raise your hand if you have paintball. Raise your hand if you have paintball. Okay, so there should be one per table. All right, raise your hand if you have candy making. There should be one per table. Raise your hand if you have electronegativity, the pollen guy. And raise your hand if you have glue. Okay, so on the top of this paper, I'm about the change seats. You see, and people put, like, are just talking over me or not following instructions. Okay, on the top of this paper, please write down 10 to 12 quality, rich comments, and that's across the whole reading. That's not on one page or the other, it's across the whole reading. So remember, that means that that's just comments, okay? So quality, rich comments, that means you're writing an annotation or a thought. You can still do highlighting and underlining and bubbling around words that you find important, but this is what I'm looking for the grading purposes, okay? Still, you do your summary of 25 words, and still you do your reflective statement of 1 sentence, okay? So I'm going to stop right now just for a moment. I'm going to give you guys 10 minutes to read. Go.
Can you put this on the board?
It's already on my website, so if the images are blurry, these are already linked under my website. You should have access to them.